frequency smoothing encryption, preventing snapshot attacks on deterministically encrypted data. It's paper by Marie-Sarah Lechartier and Kelly Patterson, and Marie-Sarah will give the talk.
Thank you. So we begin with the problem of securely outsourcing data while maintaining the ability to efficiently query it. So we have a client who wants to store some data in the cloud while being able to retrieve particular records according to some equality condition. The example I'll use throughout the presentation is of a hospital outsourcing patient records while wanting to still retrieve them based on the value of major diagnostic category, or MDC, which essentially is the reason for someone's stay at the hospital. Now, data stored in the cloud is actually physically somewhere, and it's not always clear where or who has access to it. So a natural question is, what can someone learn who sees a snapshot of this data on a disk? Now, this could be a curious cloud service provider, or it could be an attacker who breaks into the cloud service provider's facilities, whether physically or virtually, and just images the disk and sees a static snapshot of the data on the disk. So one easy way to provide some protection is to deterministically encrypt values in the database individually. Now, the client can still make equality queries. It just has to query the encrypted value of what it wants. For example, the encryption of 5 if it wants to retrieve records with major diagnostic category 5. But this equality-preserving property of deterministic encryption makes such a scheme vulnerable to a class of attacks called inference attacks. Because repetitions in the plain text will show up as repetition in the ciphertext, a snapshot attacker can compute statistics or counts of values in the ciphertexts. In particular, if the adversary knows what kind of data is stored, it can find some kind of reference distribution or auxiliary distribution. If the adversary knows, say, that the hospital is one of the clients of this big cloud service provider and is storing some data there, they might guess that this column corresponds to major diagnostic category. It can type major diagnostic category statistics into Google and get a good, rough, estimated distribution of what the value should be. And then it can simply match the most frequent ciphertext it sees to the most frequent MPC value based on the statistics it found online and decrypt records in this way. So recent work on these kinds of inference attacks based on frequency analysis has shown that they're actually devastating. These have been applied to recovering keywords in documents in the context of searchable encryption, and also values in encrypted databases, just like the scenario I mentioned before. So in particular, Naveed Kumar and Wright at CCS in 2015 examined how powerful a simple frequency analysis attack is on deterministically encrypted data. They simulated attacking the records of 200 hospitals using a reference distribution of MDC values, and they examined other attributes too from a different year. And they found that for MDC values in particular, using this very simple frequency analysis attack, matching the most frequent ciphertext to the most frequent plaintext according to their reference distribution, they were able to correctly decrypt at least 20% of the hospital's records for 75% of the hospitals. So our work looks at how to thwart these kinds of frequency analysis-based inference attacks while preserving the ability for a client who has outsourced its data to make equality queries. We present a general construction of what we call frequency smoothing encryption based on homophonic encoding and deterministic encryption. We evaluate the smoothness of the scheme both analytically and experimentally. In particular, we look at the same data attacked by Naveed Kumar and Wright, and we show that with an encoding length of just 8 bits and a statistically optimal attack using frequency information, the success rate of an adversary is reduced to just retrieving at least 20% of records on 2% of hospitals rather than 75%, even when the attacker knows the exact distribution of MDC values for that hospital. So So the inspiration for frequency smoothing encryption is homophonic encoding, which is a simple one-to-many mapping. So if we consider letters in the English alphabet, then their frequencies in natural text will look something like this, with E being the most frequent. So with a simple substitution cipher, we know that the most frequent symbol is probably E, T, A, and so on. With homophonic encoding, if we map the most frequent letters to more symbols, then we have smoothed or made the distribution closer to uniform, thus making frequency analysis much harder. So this is the idea to keep in mind as I present frequency smoothing encryption. We can simply create a scheme by composing homophonic encoding with deterministic encryption. So in a frequency smoothing encryption scheme, we consider a client that begins with an estimation of the distribution from which the messages it will encrypt are sampled, and this is D tilde. Now the client uses this estimated distribution to initialize some state, and that will determine exactly how the homophones are allocated. Messages are sampled according to some distribution D that's not precisely known. The client has just an estimation of this distribution. Then, to encrypt values, the client consults the state and chooses one of the homophones of that particular value. Back to the example of outsourced database storage. The client can still make equality queries. Instead of requesting all records where, say, MDC equals 5, it will request all records where the value is equal to any of 5's homophones. And these homophones are efficiently computable given the state. So we introduced two notions of security for a frequency smoothing encryption scheme, and these mirror the composition of a frequency smoothing encryption scheme from homophonic encoding and deterministic encryption. The first is smoothness. So the adversary gets some number of ciphertext samples, and it has to determine whether they're actual encryptions of messages or whether they're sampled uniformly at random from some set having the same size as the set of homophones. Now this isn't enough, because frequency smoothness could be achieved just by appending bit strings to messages, which grants no message privacy. So we need another notion, and that is message privacy, where the adversary gets some number of plaintext-ciphertext pairs, and it has to determine whether the ciphertexts are real encryptions of the messages, or whether they're ciphertext sampled uniformly at random from sets of some size appropriate to that message. So to attain both properties, it's enough to have a homophonic encoding scheme that is smoothing in a way similar to the frequency smoothing notion for frequency smoothing encryption scheme, and for the deterministic encryption component to provide message privacy in a way similar to indistinguishability from random bits. So this DE message privacy notion is easy to achieve with a small domain PRP or format preserving encryption or SIV mode, so we'll look at HE smoothness in more detail. One important case is where the distribution is known ahead of time by both the client, the data owner, and the adversary. In this setting, the adversary's goal reduces to getting n samples of some distribution and just trying to distinguish which distribution these samples are from, the uniform distribution or the distribution of the encoded data, which it can compute because it knows the exact distribution of messages. Using an analysis of optimal distinguishers from Benier, Junot, and Rodney from AsiaCrypt 2004, we can bound the advantage of an HE smoothness adversary in terms of the number of samples, the number of homophones, and the Shannon entropy of the encoded data's distribution. So let's look at one example of a homophonic encoding scheme that provides smoothness. This is a very simple scheme that we can't claim to have invented because it is so simple, but we couldn't find a proper name for this scheme anywhere. So the idea is to map messages to R-bit strings in such a way that each message is allocated an interval whose length is proportional to its frequency. So, for example, the MDC values, there are 26 of them, and the distribution looks maybe somewhat like this, with the circulatory category being the most frequent, accounting for about 15% of values, and burns being the least frequent. So with this interval-based scheme, the allocation of homophones with an encoding bit length of 8 would look something like this. The most frequent message gets about 38 homophones, while the least frequent would get only 1. To encode, the client would choose one homophone uniformly at random from the message's set of homophones. To decode, it needs to look up which interval the value falls in. So consider a hospital with about 130,000 records. If we want to limit the smoothness adversary's advantage to 2 to the minus epsilon, then the encoding length, using the theorem from 4 slides ago, needs to be at least 17 plus epsilon. Now maybe storage is cheap, so this doesn't matter that we're encoding MDC to 32 or 64 bits. The main problem is query extension, because each equality query, remember, is multiplied into some number of equality queries, depending on how many homophones that value has. Now, for typical cryptographic levels of security, this would probably make the schemes impractical. So we look for another way to evaluate the smoothness of a homophonic encoding scheme or a frequency smoothing scheme. And the metric we chose to use in our experiments is how many data items an adversary can correctly decrypt. We're still in a case where we assume the exact distribution is known by the adversary. The question is then, what is an optimal attack in this case? We focus on smoothness because, as I mentioned before, we can easily achieve message privacy with a pseudorandom permutation. So the technique we apply to get our statistically optimal attack is maximum likelihood estimation. We find the most likely decryption function given the counts we see of ciphertexts and knowledge of what the encoded data's distribution will be. Now, if we apply the technique of MLE to deterministic encryption, what we get is the simple matching of most frequent ciphertext to most frequent plaintext that I mentioned before. And it turns out, somewhat surprisingly, that if we apply MLE to frequency smoothing encryption, then what we get is just a very simple generalization of that. Now, although this gives a statistically optimal attack, it is limited in some sense, so it considers only proper decryption functions. In particular, it doesn't capture techniques such as the adversary guessing that the value in every single record is just the most frequent value according to the reference distribution. So here are some of our results. We looked at the same data attack by Naveed, Kumar, and Wright with deterministic encryption. So first, we replicated their results. So this is the case of deterministic encryption with an approximate distribution. For our frequency smoothing experiments, we assume that the adversary knows the exact one, but first we replicated the case for deterministic encryption where the distribution is approximately known. And this is the line going across the middle. So we can see that the fraction of hospitals for which at least 20% of records was recovered is about 75%. And for completeness, we also ran the attack when the adversary's knowledge of the distribution was perfect. So this is the dotted gray line across the top and down the side. So you get almost complete recovery of MDC values in the case where the adversary knows the exact distribution, which makes sense. Now, for our frequency smoothing encryption schemes, we tested, there were 2 interesting values. There were, well, plenty more, but these 2 show the trend. So with an encoding length of 8 bits for MDC, we see that the fraction of hospitals for which at least 20% of records were recovered drops very quickly to about 2%. If we add 2 bits to the encoding length, then the attack performs even more poorly, and we see that it's already approaching the limit. As the encoding length goes to infinity, there will be no repetitions in the ciphertexts. And essentially, we're modeling probabilistic encryption. So with no frequency information, when each ciphertext is equally likely, all the adversary can do is a kind of baseline guessing, where each message, it guesses according to the distribution. And the last line, the solid gray line, shows the performance of a simple attack. The one I said was ruled out because we consider only proper decryption functions. So this is how many records the adversary would correctly decrypt if it guessed that every single record corresponds to the most frequent category. And frequency smoothing encryption, the performance of our attack with just 8 bits of encoding is already worse than this simple attack, where the adversary just guesses that every value corresponds to the most frequent value. So frequency smoothing encryption works. It effectively thwarts inference attacks based on frequency analysis. Now the price to pay is some expansion of queries, and the client does have to store whatever decoding information it needs, which may be just a table mapping intervals to plain texts. Our paper contains more. In particular, we present another construction of frequency smoothing encryption. Rather than simply composing homophonic encoding and deterministic encryption, we build a scheme from homophonic encoding, a PRF, and an IV-based encryption scheme. Now this snapshot model, where the attacker sees just an image of the data on the disk, is very limited. A real attacker might see a lot more. For instance, it might see the queries made to the database, or it might see the access pattern. But any attack that succeeds in this setting will succeed at least as well in a more realistic setting. Since frequency smoothing encryption thwarts inference attacks based on frequency analysis, we think it will form a key part of a complete solution to secure outsourced storage. So this has been FSE at FSE. Thanks for your attention.
There's already a question in the back. Over there.
Have you looked at the effectiveness of the attack when the encryptor only has an estimate of the distribution, but the attacker has the exact distribution, which is a realistic scenario because you're encrypting the data before you need to pick the estimated solution, the estimated distribution before you encrypt the data, but the attacker can look back at last year's census.
Mm-hmm. No, we didn't explore this scenario. In some cases it might be realistic, yeah. Our framework for frequency smoothing encryption also captures the possibility of a client that updates its estimate of the distribution detail as it sees more messages, so it can slowly correct for any differences that it might have. On the other hand, we could say that it's not entirely realistic, because if the attacker can get some information, then surely the encryptor can too. So although we didn't specifically look at it, our model does capture the possibility of schemes adjusting to different distributions.
Okay, any other questions? Okay, if there's no other question, let's thank Marisa again.